If an adversary can locate a nuclear arsenal, they can destroy it. This generated radar map illustrates the paradox of visibility for traditional deterrence. Fixed land-based silos and bomber airbases are easily tracked, making them highly vulnerable to a preemptive first strike. To guarantee sovereign survival, a nation requires a secondary retaliatory force that cannot be mapped by satellites or radar, a deterrent so perfectly hidden that an adversary faces the absolute certainty of mutual destruction. This mathematical certainty is provided by a single class of machine, the nuclear-powered ballistic-missile submarine, or SSBN. Unlike attack submarines designed to hunt other ships, the SSBN is not a tactical warfighter. The sheer scale of this vessel makes it a strategic platform, built strictly for catastrophic retaliation. Understanding how this platform works requires deconstructing the engineering of nuclear stealth, the rigid mathematics of fleet rotation, and how the unique hydrology of the Indian Ocean acts as an acoustic shield. In the nuclear age, true national sovereignty relies on mastering the dark, crushing environment of the deep ocean. For decades, submarine warfare was constrained by a single chemical requirement: oxygen. Early diesel combustion engines needed atmospheric air to run, forcing submarines to remain dangerously exposed on the ocean surface. Even raising a small snorkel mast to intake air breaks the surface of the water, instantly exposing the vessel to modern radar and satellite surveillance networks. To mitigate this, naval engineers developed air-independent propulsion, or AIP. This 3D cross-section shows how an AIP system generates oxygen internally. By chemically splitting internal stores, it provides oxygen and hydrogen to the diesel engine, allowing the submarine to remain submerged. But AIP is a tactical stopgap. Within about 15 days, these chemical resources deplete to zero, and the submarine is forced back to the surface to breathe. The engineering solution to absolute stealth lies in miniaturized nuclear reactors. This diagram demonstrates how a nuclear reactor provides infinite internal electrical and propulsive power, radiating continuous energy to all ship systems, without requiring a single molecule of outside air. This allows a massive vessel to maintain speeds of 20 to 25 knots indefinitely, staying deeply submerged and entirely hidden for its entire deployment. The only limiting factor on a nuclear submarine's endurance is biological. The 150 crew members on board will eventually exhaust their food supplies. Nuclear reactors trade the mechanical limitations of combustion for absolute acoustic stealth, allowing a fleet to remain submerged until biological limits force a return to port. An SSBN weaponizes that infinite stealth by serving as a transport vehicle for vertical launch tubes, each packed with submarine-launched ballistic missiles. This animation illustrates the mechanics of multiple independently targetable reentry vehicles, or MIRVs. After launching from deep underwater and breaching the atmosphere, a single missile splits into multiple distinct warheads, branching out in different directions. A single hidden submarine can launch dozens of these warheads simultaneously. By striking up to 12 distinct targets per missile, this volume easily overwhelms land-based missile defenses. To make this terrifying payload a credible deterrent, a Navy must operate under a rigid doctrine known as continuous at-sea deterrence, or CASD. This cyclical flowchart shows the strict mathematics of CASD. A sovereign Navy requires a minimum rotation of 4 SSBNs, 1 undergoing maintenance, 1 in training, 1 transiting to port, and 1 actively hiding on deep-water patrol. Because of this continuous rotation, every single day of the year, an adversary is mathematically guaranteed to have zero intelligence on the exact location of the active patrol boat.
However, if the patrol submarine is somehow tracked by an enemy hunter-killer ship, it must defend itself violently to protect the nuclear payload. For this, the SSBN relies on heavyweight acoustic homing torpedoes. These weapons utilize advanced wake homing and wire guidance systems to track the acoustic signature of a pursuing ship. A single hit delivers enough explosive force to physically break a surface vessel in half. This combination of MIRV payloads and a rigid fort-ship rotation ensures that any adversary launching a first strike faces guaranteed catastrophic retaliation, paralyzing their ability to initiate conflict. But the engineering of the submarine is only half the equation. An SSBN is only as invisible as the body of water it hides in. Adversary navies face severe geographical disadvantages.
For the Chinese PLA Navy to deploy into the Indian Ocean, their submarines must transit roughly 8,000 kilometers from their home ports.
This topographic map highlights how foreign submarines are forced to pass through incredibly narrow, shallow maritime choke points, specifically the Malacca, Sunda, or Lombok Straits. Navigating these coastal shelves forces deep-water submarines to rise perilously close to the surface, instantly triggering radar and sonar nets, and stripping away their primary advantage of stealth. India capitalizes on this geography by utilizing the Andaman and Nicobar Islands as a permanent tri-service watchtower, looming directly over these critical maritime gateways. Once inside the deep ocean, tracking a submarine requires mastering underwater domain awareness. Electromagnetic radar is useless underwater, leaving sonar, the propagation of sound, as the only reliable sensor. This is where the unique hydrological profile of the Bay of Bengal acts as a natural bastion for Indian SSBNs. This cross-section view shows massive regional rivers pouring billions of gallons of fresh water into the salty ocean, creating extreme gradients of salinity and temperature. This acoustic propagation model demonstrates the physics of those gradients. When an enemy sonar ping hits the boundary between warm, fresh water and dense, cold, salty water, the sound wave does not travel straight. It bends, refracts, and scatters. This severe refraction creates massive acoustic shadows in the deep water. An SSBN can loiter within these blind spots, completely undetected by surface ships listening above. Strategic deterrence weaponizes the unique hydrology of the ocean, using geography as a force multiplier for the submarine's physical design. Constructing India's indigenous Arihant-class submarines required a staggering 50-year journey of industrial and scientific commitment. The SSBN represents the successful convergence of three highly isolated disciplines: miniaturized nuclear reactors, cryogenic rocketry, and advanced acoustic weapons. Possessing this sovereign platform, insulated by the Bay of Bengal's acoustic shield, permanently removes the threat of foreign nuclear blackmail. Yet the future of maritime warfare points toward eliminating the single remaining vulnerability of the SSBN, the biological limits of the human crew. What happens to global security when we remove the humans from the nuclear submarine? Naval doctrine is now shifting toward the deployment of robotic platforms, extra-large unmanned underwater vehicles, or XLUUVs. Mating a miniature nuclear reactor to an autonomous drone creates a platform capable of lurking in the ocean's acoustic shadows for decades at a time without ever needing to surface for air or food. As long as the deep ocean remains opaque, the ultimate arbiter of global power and sovereign survival will remain the silent, hidden machines patrolling its depths.